Hello, everyone, and good evening. My name is Mark Boharnwa. Thank you for joining us for tonight's ASRC Falconer Lecture as we close out a successful summer 2022 lecture series. Tonight's lecture is Zoom only, and your video and audio have been disabled. As always, if you have a question for our speaker, please type it into the Zoom chat feature, and all those questions will be addressed during the Q&A session by your lecture host, Dr. Craig Ferguson. It is my pleasure now to introduce Dr. Craig Ferguson, Research Associate and Falconer Lecture Chair at the Atmospheric Sciences Research Center. Craig will introduce tonight's speaker and will moderate the Q&A session after the lecture. Craig?
Thanks, Mark. Good evening, everyone. It's my honor to introduce Dr. Patricia Parker, a research scientist at NASA Goddard Space Flight Center in Greenbelt, Maryland. I first met Patricia in 2015 when she was finishing up her Ph.D. in climatology at the University of Delaware. Since then, her research quickly propelled her to the top of the international modeling community. She is the newest elected member of a World Climate Research Program panel on global land atmosphere systems. And for that panel, she leads a project on irrigation with International Operational Weather and Climate Modeling Center partners. Patricia is one of the top experts globally on the subject of satellite remote sensing of large-scale irrigation. Her research addresses the need to improve our understanding of regional agricultural water demands from a national water and food security standpoint, but also from the perspective of human involvement in the climate system. Her work is an exciting example of societally relevant applications for NASA's most advanced Earth observing systems. Please join me in welcoming Dr. Parker.
Thank you so much, Craig, for that far too generous introduction. That was really, really very kind. And I really appreciate the invitation to talk to all of you tonight. I wish that I could have made it in because the Whiteface Mountain Observatory seems amazing. So I really hope to be able to visit it one day and visit your main campus sometime as well. So as Craig mentioned, tonight I'll be talking about the monitoring and modeling of irrigation, which may not sound very important or even particularly relevant at first glance to the weather community or to weather forecasting. But I hope that by the end of my talk, you'll have a new appreciation not only for irrigation, but also for the land surface in general and how it can be really helpful in predicting and understanding our weather and climate. So in order to understand how the land affects the atmosphere, we have to first understand the planetary, or some people say atmospheric boundary layer. So this is the lowest layer of the atmosphere. It's where we live, and it is directly influenced by Earth's surface, and really quite quickly. It generally responds to surface forcing within about an hour or less. Most of you have probably boiled a pot of water at some point in your lives, so you know that you can't fill the pot all the way to the top because once you heat the water, it'll become less dense and expand. You'll get a lot of bubbles and turbulent mixing within the pot, and that will push the water level in the pot higher, hopefully not overflowing the pot if you've accounted for that expansion to happen. The planetary boundary layer is in some ways quite similar to the pot. Our energy originates from the sun, but the atmosphere is a fluid and it's heated from below by the Earth's surface, just like the pot is heated from below by the burner. So when the sun comes up in the morning, it heats the land, which heats the air directly above the land, causing it to warm, expand, and rise. And that causes a lot of turbulent mixing of the air and pushes the top of this really well-mixed layer that we call the boundary layer higher and higher, just like the water level in that pot. It's hard to see this mixing happening, but you might have experienced it. If you've ever been in a plane and taken off or landed, especially on a sunny day in the afternoon, you might have felt a lot of shaking and bouncing of the plane while you're in the boundary layer. And then all of a sudden, it just kind of smooths out once you're above the boundary layer. Now, the characteristics of the land can play an important role in determining how much heat and moisture is in the boundary layer. And that affects not only the height of the boundary layer and its stability, but also those things feed back and can affect clouds and rain development. So if we, for example, replace our grass patch with a city, then the sun's energy will go primarily into raising the temperature of the land, making it warmer and generally creating a drier and taller boundary layer. The opposite is true. If instead we replace the city with a cornfield, then the land is probably going to be quite a bit wetter, and more of the sun's energy is going to go into evaporating water rather than raising the temperature. Plus the corn will probably kind of exhale a little bit of moisture as well. So the boundary layer in this case will be cooler, more humid, and the top of that layer will be shallower or closer to the Earth's surface. So we know that these processes are important for predicting the weather. That's why our operational weather models include a land use, land cover data set, and usually a land model. And the model treats different types of land types differently in terms of how it calculates radiation and the physical properties. So the heat and moisture and wind flow above a forest will be different than over a city, than different over a grass patch. Now, a major missing piece in most of our operational weather models and climate models is any type of human water management, like irrigation. Even though it can really drastically change how much water is available and therefore how much heat and moisture is supplied to the boundary layer. So our group at NASA has implemented irrigation in our research models, and we've been working to better understand how that added water from irrigation can affect weather and climate. It might seem like irrigation is only a minor factor in the weather budget, in the water budget, but it actually accounts for 42% of all freshwater withdrawals in the US. In this map from the USDA that shows acres of irrigated land, you can see that irrigation occurs from coast to coast and from our northern to our southern borders. In the eastern US, the irrigation is a little bit more concentrated into specific areas. The eastern US is more humid and gets more rainfall, so you typically don't need irrigation to grow crops in most of these areas. The irrigation is more so to kind of increase yield. It provides a buffer in case there's a dry spell, especially during like a critical phase of the crop's growth. It can supplement the soil moisture and make sure that the crop is really healthy and continues to have good yield. So often in the eastern US, you'll see rain-fed and irrigated crops right near each other. In this Google Earth image from eastern Nebraska, you can see the darker green towards the left side of the image. That is predominantly irrigated crops. But it doesn't look so different visually from the rain-fed fields around it. If you weren't looking closely for it, you might even miss this distinction. However, in the Western US, it's a completely different story because they really don't get a ton of rainfall. So here, irrigation is generally required to grow crops. And that makes for a really dramatic difference between the irrigated area as compared to what would be there naturally and what is surrounding the irrigated area. When we look at the US as a whole, irrigation has grown pretty steadily since the late 1800s, but it's kind of leveled off in the last several decades. This can vary a lot though by region. A lot of the central US that has a lot of groundwater reserves, there's more abundant water resources there for irrigation. And so we've seen some areas of the central US continue to grow their irrigation acreage, whereas in the West, where there's not a lot of rain, there's been a lot of droughts, and there's a lack of availability of water, There we've seen some loss in the last several decades. So we can't irrigate if there's no water available to irrigate. And these trends vary a lot based on where you are in the country. One area of the US that has had a particularly interesting history regarding irrigation is the Columbia River Basin in central Washington. So this was the site of the Columbia Basin Project, which was a federal government program in the early 1900s to try to get people to move to the Western US and develop the West so that even more people would want to live there. The plan was to build a series of dams and canals that would deliver water for irrigation from the Columbia River to the land that surrounds it in central Washington. It was first authorized by President Roosevelt in the early 1930s, but it took a while to come to life, as is often the case with both large construction projects and anything related to the federal government. So Congress finally authorized the project in 1943, but the construction was delayed until after World War II. So the first deliveries of water didn't occur until between 1948 and 1952, depending on your location within the basin project boundaries. And once that water was delivered, it really helped to turn this otherwise kind of barren landscape into a very agriculturally productive region where people did want to move and live. So this project provided a really interesting opportunity for us to look back at the historical climate record to see if this rapid expansion of irrigation in central Washington had any discernible impact on temperatures in that region. It really doesn't occur too often in the earth sciences that we have a pretty major land use change like this that happens really quickly, is documented really well, and we have weather or climate observations available in the area at the same time. So those things all kind of came together really nicely for us here. So we looked at 7 global historical climate network sites within the vicinity of the Columbia Basin Project. So those are shown by the by the yellow dots and letters. And the Basin Project boundaries are shown in the black line there. And the idea was basically to look at temperatures before and after the irrigation expansion and see if it had any effect on our maximum summertime temperatures in this region. And if we did see an effect, either warmer or cooler temperatures, we then wanted to use our regional weather model to better understand the wind flow patterns and kind of mechanisms that might lead to the effects that we see in the temperature record. The USDA records irrigation acreage by county, going all the way back to the late 1800s. They usually take an inventory every about 5 years. And so that's plotted in the graph that you see there on the right. And the line colors here correspond to the county outlines on the map on the left. And those are overlaid on present irrigation extent, which is shown there in the gray. So you can see that there is a pretty dramatic increase in irrigation after the completion of the Columbia Basin Project, especially in Grant County, which I've highlighted here in red. Grant comprises really the bulk of the Columbia Basin Project within its boundaries. And so that's why we see this steep increase there more than in any of the other counties. And so we use this graph to help choose our before and after irrigation periods for our temperature analysis. So we chose 1908 to 1938 as a 30-year period before the start of irrigation, and 1968 to 1998 as our after irrigation period. And that's to allow, irrigation time to ramp up and the effects to be felt. So we compared these 2 30-year periods by plotting histograms of all daily high temperatures for each 30-year period. So each bar is showing the number of days where the high temperature for that day falls into that bin or that range of temperatures. The solid bars are the before period, and the hatched bars are the after irrigation period. And so what we see at most of these sites that are colored, and I've colored them in blue, there is a shift in the distribution of temperatures to the left, which is towards cooler temperatures after the expansion of irrigation. And the average high temperature for these periods after irrigation is cooler than before irrigation. So that makes us think that it's possible that irrigation is contributing to cooling temperatures in this later period. However, you could argue that just because this later period is cooler, that doesn't necessarily mean that it's a result of irrigation. This later period just could be a naturally cooler period in the climate record. And that's a fair point. And so to investigate this further, we looked at the regional climate anomalies for the entire Pacific Northwest US. And in the winter, these anomalies show that the after irrigation period is warmer. And all of our climate network sites locally in the CBP region, they also show that the average temperature in December, January, February is warmer in this period after irrigation. So in this case, our local signal, our local temperature signal agrees with our regional climate signal that this later period is warmer. During the summer, our temperature anomalies at the regional scale are again warmer in the later period, but this time our summer maximum temperatures in, sorry about this. Of course. Alrighty. There we go. So the summertime maximum temperatures in this later period locally are cooler in the later period. So that means that they disagree with the broader scale climate signal. And that gives more weight and more support to the fact that this local temperature signal is probably being driven by irrigation turning on, in this mid-century period as a result of the Columbia Basin Project. Just to be sure though, and to further explore the drivers of this cooling, we used our NASA version of the Weather Research and Forecasting Model, or WRF, to simulate a few different fair weather days in July. So the panel on the left shows the irrigation cooling effect, basically the maximum difference in temperature between our simulations with irrigation and without, as simulated by the model. And the rightmost panel, July 23rd and 24th, that is kind of most representative of the typical wind flow pattern in the summer in this area of Washington. So the winds tend to be from the southwest. And under that wind flow pattern, the model shows that our irrigation cooling effect can reach as far downwind as every station that showed cooler temperatures in the climate record. We can also take a cross-section of this region and look at the temperature and humidity changes in the lower atmosphere and the boundary layer. And so that's what you see on the right here. This is an animation of each hour of the model simulation, showing that when irrigation is included in the model, we have a shallower boundary layer that kind of caps the irrigation effect. It makes it cooler and more moist close to the boundary, close to the surface. And as the day progresses, the boundary layer grows And that cooler and more humid air is able to be transported downwind to the Global Historical Climate Network sites. And so overall, we were able to show with this work that irrigation likely cooled summertime high temperatures in central Washington. So this study is just one example of why I believe irrigation should be included in weather and climate models. But in order to do that, at least in order to do it well, it requires critical information not only about irrigation practices, such as where irrigation is occurring, when it's occurring within the season, and when does it start in the season, when does it end, how much irrigation water is applied, and what type of irrigation it is. Is it sprinkler? Is it flood? Is it drip? All of those are important features to know to get into the model. But in addition to those, that human practice information, it's also important to know what the impacts of irrigation are on the boundary layer under different atmospheric circumstances. And it has historically been really hard to get this kind of information. Most farmers don't really want to let nerdy scientists into their fields to set up instruments that will get in their way as they take care of their fields, and maybe even track their water use in some cases. That's not really an attractive proposition for a farmer. So in the past, it's been really difficult to be able to get this kind of data. But recently, there have been a couple of field campaigns, as well as advances in satellite technology that may help us get information about irrigation that can be useful for our models. So in the remainder of our time together, I'm going to talk about a couple of those field campaigns and some satellite observations that we think will prove promising to help us include and improve irrigation in our weather and land models. So GRAINEX was the Great Plains Irrigation Experiment, and it was a field campaign funded by the National Science Foundation. The goal of GRAINEX was to observe impacts of irrigation on the weather in eastern Nebraska by looking at differences between irrigated and non-irrigated regions. And in the study region of eastern Nebraska, the Big Blue River is kind of like the unofficial dividing line between irrigated fields to the west and mostly rain-fed fields to the east. The campaign took place in the summer of 2018. And as part of the campaign, they deployed about 80 temporary met stations to measure things like temperature, humidity, and wind. There were 12 flex towers, about half on each side of this irrigation divide. There were 2 sites where they launched weather balloons and had vertical wind profilers. And then for a couple of weeks in June and July, they also had Doppler radar on wheels from NCAR deployed to a few different sites in the northern part of the study area. And there were additional weather balloon launches then as well. So we call these intensive observation periods. There was one in early June that was supposed to be kind of before irrigation really kicked off too much. And then another in kind of mid-July to get the kind of peak of irrigation and likely irrigation impacts. A couple of my colleagues and I were able to visit a few of the sites early in the GRAINEX campaign. So this is what it looked like on the ground during GRAINEX. These are the irrigated and non-irrigated flex sites. And so these instruments measure the amount of heat and moisture being transferred from the surface to the atmosphere. And you can see that in some cases, they actually were able to get these instruments into the fields. We also visited the Doppler on wheels. So this is a mobile radar owned by NCAR. And this particular Dow is Dow 6, and Dow 6 was on the Discovery Channel's show Storm Chasers back in the day. So that was really exciting for me because I used to really like to watch that show. And I was super excited to see Dow 6 in real life. I have a quick video here. So you can see the radar kind of scanning. It's supposed to scan 360 degrees, but it wasn't quite working exactly right while we were there. And it was much louder than I expected it to be also, but I guess that makes sense because it takes a lot of power to power such a large instrument. You can also see the helium tanks there that were used to launch weather balloons. And we were able to be there for the launch of a weather balloon. My colleague Alicia was actually able to help with the launch. So I think that was a lot of fun for her. And at this site and the other Dow sites, they launched weather balloons every 2 hours during the daytime during this special 2-week period in June and also later in July. The first studies using data from GRAINEX are starting to come out now. If you're interested in learning more about the field campaign, there is a really nice article in the bulletin of the AMS that gives a general overview about what kind of observations were available and does some very preliminary analysis on the data. And then since then, much more recently, there have been a couple of other papers that came out that look into much more detail, look at the observations in much more detail. And overall, the campaign was a success, and the data do show in these first studies that irrigation does have an impact on fluxes, on temperature, moisture, and mesoscale circulations in this area of eastern Nebraska. There was another recent field campaign in Spain in the summer of 2021 that was also focused on observing irrigation's impact to the atmosphere. It was called LIAISE, and they also deployed many, many different instruments in irrigated and adjacent non-irrigated areas. This is actually a really nice complement to the GRAINEX field campaign because the climate is so very different in this region as compared to Nebraska and GRAINEX. Nebraska is much more humid, it gets more rainfall. And so again, you kind of have that rain-fed area next to the irrigated area. Whereas in Spain, this is a much drier area. And so there are really drastic differences between the irrigated area and the surrounding area. So it provides a nice complement and contrast to the data that was collected during GRAINEX. Irrigation makes the soil wetter. So observations of how much water is in the soil, which we call soil moisture, can give us information about irrigation. And that information is particularly useful to our models since soil moisture is an actual variable in our land and weather models. The most traditional way to measure soil moisture is with a soil probe in a field, but there are other more fun ways that we can do it as well. Trenton Franz at the University of Nebraska-Lincoln has an instrument called a cosmic ray neutron probe, and it's mounted actually into the back of a pickup truck. And so he, or more likely his students, are able to drive it along a road and get measurements that they're able to convert into soil moisture. And it's not just directly under the truck. They are able to get a footprint a little bit away from the truck so that they're able to make these maps of distributed soil moisture, which are really valuable, especially for our models. There are also instruments that can be mounted onto planes to measure soil moisture. My colleague Ed Kim at NASA has 2 instruments. One is called GREX and the other is called SLAP. And so he was able to mount GREX onto a NASA plane and use it for the GRAINEX field campaign. And I believe he used SLAP during liaise as well. And those instruments also give a distributed map of soil moisture. An example there is shown beneath the plain picture. So both of these are really useful for our modeling. We can also get irrigation information from satellites in space. So NASA has the SMAP, or Soil Moisture Active Passive Satellite, and it measures soil moisture by observing microwave radiation. And then there is an algorithm to convert that to soil moisture. SMAP was designed to have both active and passive remote sensing technology. So passive means that the instrument is just kind of sitting back and taking in signal, and active means that it is actively doing something. So radar is an active remote sensing technology because it sends out a signal and waits for that signal to be returned. So SMAP has a radiometer, which passively receives microwave signals. And then it also has a radar. And each type of instrument has pros and cons. And the idea of SMAP was to combine both measurements to kind of get the best of both worlds and leverage the advantages of both types of data. Unfortunately, the radar stopped working not too long after launch, but we do still get great data from the passive part of the satellite. So it's still a great satellite. And another great thing about using microwaves to get soil moisture is that they can be detected through clouds. So even on a cloudy day, we can still get observations of soil moisture from SMAP. So not too long after the SMAP satellite was launched, the data was coming in and it was looking great. We were really curious about whether we could see any evidence of irrigation in the SMAP observations. So we looked at 3 areas of the Western US, but I'll just show one example from Northern California. And this area is near Sacramento, and it is huge for rice production. About 95% of California's rice comes from this area, and rice requires a ton of water. So you can see in these pictures just how the rice agriculture really just completely dominates and takes over the entire landscape. And because it uses so much water, if SMAP wasn't able to see this, then it's very unlikely that it could see something, much more subtle like drip irrigation. So this was kind of a good test of the satellite capabilities. So we compared SMAP measurements from within the irrigated area to those outside of it. And so that's shown in the chart here on the right. The blue dots and lines are soil moisture measurements from within the irrigated area, and red is outside of it. And during the winter, when it's the rainy season, both the both the irrigated site and the non-irrigated site are both very wet, and they kind of behave similarly. So their peaks and valleys are kind of moving in the same way. It's wetting and drying down according to the rainfall. But when the rains end late in the spring, the non-irrigated site dries out, kind of consistent with that rainfall signal, the rainfall decreasing. But the soil moisture at the irrigated site actually increases, and then it stays wet throughout the beginning of the growing season of rice. It only starts to fall as the rice grows and grows out of the water and starts to attenuate some of that signal getting to the satellite. And then once it's harvested and the rainfall returns, the two sites then they behave similarly again as we get into the late fall and the winter again. And so this was pretty good evidence to us that SMAP is able to detect irrigation in this area. And we saw similar results in the 2 other areas that we looked at in the Western US. So this was an exciting development and has exciting prospects for getting irrigation into our models in terms of data assimilation and other types of capabilities. soil moisture isn't the only useful observation we can get from space when it comes to looking for irrigation information. The temperature of the land, which we call the land surface temperature or LST, does a really great job of showing irrigated areas because they tend to be cooler than similar areas that are not irrigated or even other types of land use. So we get LST observations using satellites that measure in the thermal infrared band. And two examples of that are EcoStress and MODIS. A big advantage of these types of observations is that as compared to soil moisture, they're pretty high resolution. So soil moisture observations are great, but they can be kind of coarse, at the scale of 10 to 40 kilometers. So it's kind of like watching an old TV that's standard definition, or even like an old show or video from the 80s. Like, it's useful and you can enjoy it. You can see what's happening, but it's a little bit fuzzy. The LST observations are like watching high definition, where you can really see a lot more detail. The drawback is that it's measuring an infrared temperature. So if there are clouds in the way, the satellite will measure the temperature of the clouds instead of the land. So it's really limited to only being useful on clear days. So here's an example, again, pulling from the Columbia Basin region of central Washington. And you can see how this area looks in a visible satellite image there on the left. And then how EcoStress, which is land surface temperature, MODIS, again, land surface temperature, and SMAP soil moisture observe this region. And so you can see that irrigation is apparent in all three of these data sets. There is wetter soil or cooler temperature over the area that we expect to be irrigated. But with LST and especially with EcoStress, you can really see much more of the detail and even almost down to the field scale. Because EcoStress is so high resolution, we're hoping to use it to better understand irrigation practices. So this is, again, zooming in on an even smaller region of the Columbia Basin. And if we look at land surface temperature for the same area about a week apart from EcoStress, we can see fields that are consistently watered. Those show up as cool in both images. And that's in contrast to other fields that are warm this week, but cool the next week. And so that implies to us that these fields are being managed differently, whether it's because it's a different farmer or it's a different crop. But water is being used differently from one field or from one area of this image to the other. And that type of information is really important and useful for us when we try to model irrigation, because we want to know how much water farmers are using, how they're applying irrigation, so that we can try to make our models as representative as possible of the real life processes. So to wrap things up, I hope that I have maybe convinced you a little bit that irrigation is important to weather prediction and that it should be included in weather and climate models. The atmosphere is bounded by the land. This is where we live, and the things that we do here can impact the weather. That certainly isn't to say that those things are quote unquote bad, or that we should stop doing things like using irrigation or building cities. That's certainly not what I'm advocating for at all. It's just important to understand the impacts of those activities and to account for them in our models so that we can better predict the weather. This general idea, I think, is gaining a little bit of steam recently in kind of the popular media. So I've seen a lot of articles in the past few weeks about corn sweat, which is referring to the extra humidity that's put off by corn when it takes in carbon dioxide and exhales water. So that's not necessarily irrigation specific, but it is certainly an effect that is intensified even more when irrigation is used. And it kind of acknowledges this broader point that our land use choices can affect the weather, and even in this case, can affect our comfort. So that's all that I have. Thank you so much for your attention, for being here, and thank you, Craig, for the invitation. I really enjoyed kind of putting this presentation together, and I'm glad to take questions. You can also feel free to email me at my email address there as well if I don't get a chance to make it to your question. So thank you.